Welcome to ECE 302. This is lecture 4.3 on cumulative distribution functions. I'm Professor Stanley Chan. So today we are going to look at a very interesting topic. It's called the CDF. We have actually learned about the CDF when we talk about discrete random variables. I'm not sure if you still remember the topic. So in this section, we are going to revisit this topic again from the perspective of continuous random variables. There are three things we want to discuss for this CDF. One, what is CDF? As you can see in this slide, I'm defining the CDF as this very simple definition, that the CDF of a random variable x evaluated at this x is just the probability that this random variable is less than the state. So this is a very simple definition, but how do we understand this definition? We're going to discuss the definition and its interpretation. And then second, we're going to learn about the properties of the CDF. There are altogether 6 properties we want to go through together. Lastly, we want to talk about the relationship between a CDF and a PDF. Knowing this relationship will help us translate from CDF to PDF and from PDF to CDF. So let us start by first defining the CDF and go through a few examples so that we understand what they are and what they can do. The definition of a CDF is as follows. You have a random variable x, and let's assume that it is a continuous random variable because we have already discussed the discrete random variables. For the continuous random variable, the CDF is defined as this probability where this random variable x is less than the state x. And since it is continuous, we can also write it as the integration of your PDF, and we want to integrate from minus infinity to x. Now, of course, when we write the x in the limit, we want to make sure that we don't have a confusion in terms of the notation. So typically, we will write it as x prime, dx prime as the dummy variable. Or sometimes we can also even write it as integration with respect to a t. Okay, so t doesn't show up in the output here. So what is this fx? Well, this fx, of course, it is specified by the random variable x. So we're looking at the CDF of a random variable x. This x has to match with this x here. And this x stands for the upper limit of your integration. Now, let us look at this integration carefully. This integration says that I have a function fx, small fx, okay? And then its dummy variable is t. So now I want to integrate this function from minus infinity all the way to x. So let's imagine that we have a function. So this is a PDF. This PDF, of course, it has to be positive. And then we're integrating from minus infinity all the way to this point x. Okay, so here is from minus infinity to x, and this is the dummy variable t. So I'm integrating this function from minus infinity to x. That will give me the right-hand side of this definition. And then on the left-hand side, it is a what? It is a function of x, right? Because if I integrate this function of x of t from minus infinity to x, then the resulting value would be a function depending on t. Because if I move the x to the left or to the right, then I will have a different value because the area under the curve becomes different. And so it becomes a function of x. And on here, I am plotting a function of x. Okay. So if I am changing my value of x, then the area the area under the curve of this function will go up. Okay. Now, as I move x from this point to this point here, then I am moving this fx, this capital Fx, from here to here. Now, notice that because I am integrating the function, the area under the curve has to go up. It has to always go up. The reason is that this is a PDF, and by the definition of a PDF, it cannot go down. Okay, it cannot give you a negative value, and therefore, the more I integrate, the more CDF values I will get. So this is the definition of a CDF, and you can see that it is really just the cumulative sum of this PDF. By cumulative sum, I mean that I'm integrating from minus infinity up to the point that I'm interested in. Okay, so the relationship from the PDF to the CDF is an integration, and you can easily imagine that the way to go backward is a differentiation, okay, which we will discuss later. So this is the definition of a CDF, and you may wonder how CDF can be useful in data analysis. It turns out that CDF are very, very useful tools for us to compare distributions. CDF also help us to generate random variables, which we will discuss in a later lecture. Now, let us spend a couple minutes to understand a few examples so that we know how to manipulate the CDF. The first example is a uniform random variable. This random variable has a PDF given by this equation. It's fx equals to 1 over b minus a, where a and b, they are the upper and lower limits of this random variable x. The picture of this PDF is shown here, where you have a 0 everywhere until you hit a, and then you go to a constant level, and it stays constant until it reaches b, and then it becomes 0 again. So this is the PDF of the random variable x. The height of this PDF is 1 over b minus a, because you want to make sure that the PDF integrates to 1. So this is a PDF, and our goal is to find the CDF of this PDF. So how do we do that? Well, we know that the CDF, this fx, is the cumulative sum of the PDF. By cumulative sum, we mean that we want to integrate from minus infinity all the way to the point of x where we're interested in. So the definition of this fx is the integration from minus infinity to x of fx of t dt. Okay, again, this t is just a dummy variable for the integration. After the integration, the t will be gone. So how do we evaluate this integration? This integration, according to this picture, we want to substitute this fx of t by 1 over b minus a. Okay, and then we want to integrate this function with respect to t. Okay, now there's no t in this function, this PDF, because the PDF is constant. Then we want to worry about the upper and lower limit of this integration. You're not just integrating from minus infinity to x, you're integrating from a all the way to x. Now note that the lower limit is a because I do not have anything where x is less than a. Okay, so the starting point has to be a. Anything that is smaller than a, you have 0 over here. The upper limit is not b, because if you put a b here, you're integrating the entire PDF, you will get 1. The upper limit is x because I'm interested in evaluating this PDF from the lower limit all the way to the point x, which is the point that I'm interested in. So you put this upper and lower limit into this equation, and then you can start to calculate this integral. And this calculation is just simple calculus. Okay, how do we do that? Well, this integration is 1 over b minus a, and then it's a constant, so you can pull out from the integration. And then you have this t. This t, we want to evaluate the lower limit to be a, the upper limit to be x. and then this integration would be x minus a divided by b minus a. Okay, so just a very simple calculus for this integral, you can get the solution. And so that gives you the result for this, which is x minus a divided by b minus a for any x that is between a and b. Now you can see that here I am very careful in terms of writing down the CDF. I also specify the CDF value when x is less than or equals to a and x is bigger than b. Now why do I do that? Well, because the CDF is defined for all the x along the entire real line. And so if I only specify this range, I haven't really specified the thing before and after. So I need to specify that. The thing before is 0 because when x is less than a, then you are just integrating anything less than a, and that will be 0 because your PDF is 0. When x is bigger than b, you're integrating the entire PDF, so you get 1. So that's the reason why we have this a and b and between a and b. Okay, so now we have learned the first example about uniform random variables. We want to ask, can we do something a little bit more difficult where this PDF is not a constant function? So this goes to the second example, which is example on exponential random variable. In this exponential random variable, the PDF is given by this equation. Now, of course, we haven't learned about this exponential random variables yet, but we can still use this formula. This exponential random variable has this equation lambda e to the power minus lambda x for x bigger than 0 and is 0 otherwise. We want to find the CDF. So how does this PDF look like? The PDF looks like this. It is an exponentially decaying function as a function of x. As your lambda grows, then it will just decay faster. And if your lambda becomes small, it will decay slower. So this is the shape of your fx. Now, you want to find the CDF. The CDF is the cumulative sum of the PDF. And then the cumulative sum of the CDF has to integrate all the way from minus infinity to the point x, which you are interested in. So how do we define it? Well, it's the integration from minus infinity to x of your fx. Now I change the variable to t because it's a dummy variable. And then how do we calculate this integration? Well, this integration is can be rewritten as lambda e minus lambda t of dt. How about the limit? The lower limit is actually 0 because you are this function is starting from 0. Anything less than 0 is 0. The upper limit is x because I want to evaluate my CDF at x. So this is the integration that you're interested in. And then I'm skipping a lot of calculations. And if you follow all these calculus, then you can reach to this conclusion where this integral will give you 1 minus e to the power minus x. And then now this is only true for this range. Okay, it's true for the range that x is bigger than 0. For the x that is less than 0, you get 0. Why? Because when x is less than 0, you're just integrating 0 from minus infinity all the way to 0. And so that will give you 0 always. Okay, now how does this CDF look like? This CDF look like this. So you can imagine that I'm integrating this function all the way from 0 to the point x. And so now in the beginning, I am integrating this function. I have a lot to integrate, and so it rises. But towards the end, if my x increases, then the increase in the CDF value becomes less and less, and eventually it saturates. Where does it go to? It goes to 1, because the CDF cannot be bigger than 1, since the CDF evaluated at plus infinity is just that you're integrating the entire PDF. So it will go to 1. Okay, so now we're in a good position to talk about some properties of the CDF. There are altogether 6 properties of the CDF. And here I'm listing the first 3 on this slide. The first property is that the CDF is non-decreasing. Why? Because you can see that since this is my PDF, the PDF is always positive. When you do the integration to calculate the CDF has to always go up. Okay? The only way for the CDF to go down is that your PDF has a negative value because you're integrating the area. But this is not possible because the PDF is always positive. So this is clear. Now, the second property is also very, very easy to understand, that the maximum of the CDF happens when x goes to infinity. Okay, and this value is that fx evaluated at plus infinity is 1. This is true because when you integrate the entire PDF, you will indeed get 1. The minimum of the CDF happens when x equals to minus infinity. Why? Because if you're evaluating the CDF at minus infinity, that means you are just integrating this PDF from minus infinity to minus infinity. That is 0. So these two are also very clear from the picture. Now let us talk about property number 4. This property says that if x is a continuous random variable and if CDF is fx, okay, is continuous at this interval, then the probability that x is between a and b can be easily written as the difference of fx evaluated at b minus fx evaluated at a. Now, how do we understand this? Let us draw the picture. Okay, so let's say this is my PDF. Okay, and then I want to evaluate the probability from the range of A to B. Okay, now how do we do this integration? Well, of course, this integration is the integration from A to B of my fx of t dt. But this integration can also be written as from minus infinity to b of fx of t dt and minus infinity to a of x of t dt. Now, why is that? Well, this is because this function can be written as the integration all the way to b, okay, from minus infinity all the way to b, and then subtract this function. Okay, so this is the same function. And then you just evaluate it all the way to a. Okay, so you can see that here is the area under the curve up to b minus the area under the curve up to a. So if you take the difference will be here. Okay, so that explains why we have this equation of integration from minus infinity to b minus the other integral from minus infinity to a. Okay, and this is precisely just f at b minus f at a. So this is property number 4. Property number 4 says that if I want to evaluate the probability, I just take the difference between the CDF. On the CDF, how do you see that? Well, the CDF is an increasing function, right? And therefore, and the difference between b and a is just that I have this point here, which I have a value of f at b, and then I have another value, this is f at a. The difference from this point to that point in terms of height, that will give you the probability of x is between a and b. Okay, so that is the pictorial explanation of this equation. So let's work on one example. So again, let's use this exponential random variable. The PDF is given by this equation. The CDF is given by that equation. We want to find the probability that x is between 1 and 3. I have two approaches. One is the PDF approach. The other one is the CDF approach. the PDF approach says that I want to integrate my lambda e minus lambda x. This is my PDF, and then the limit will be from where? Well, since I'm evaluating this range, I want to evaluate from 1 to 3. Okay, and then you do all these calculus, and then you can show that it equals to e minus 3 lambda minus e minus lambda. How do I solve the same problem using the CDF? Since you are already given the CDF, calculating this will actually be quite easy. What you do is that you use the CDF formula. You say that, okay, I am evaluating my x from 3 to 1. So I first calculate the CDF at 3, and then I minus the CDF evaluated at 1. Okay, then what do you do? Well, then this is just 1 minus e minus lambda 3, and then here this is 1 minus e minus lambda 1, and you plug in the number, and then you can get this equation. So this is how we calculate this probability using a PDF. This is using a CDF. Here is another example where in this case we are given this PDF where this PDF is 2x for x between 0 and 1 and 0 otherwise. We want to find the CDF, and we also want to find this probability. Now, before you work on a problem like this, what you should do is try to draw the picture of the CDF, the PDF. This is a very simple PDF where your range of x is going from 0 to 1. We know that it is 0 otherwise, so for anything that is less than 0 and is bigger than 1, they're just 0. Now, for things that is between 0 and 1, you can see that the PDF equation is 2x. 2x is a straight line. Okay, it's a straight line with a slope of 2. So this is the PDF. This is your fx of x. Okay. Now, if this is the PDF, we ask, how will the CDF look like? According to the definition of a CDF, this is just the integration from minus infinity all the way to x of fx of t dt. That is the definition. Now, if I plug in the PDF, this is 2 times t. I replace the x by t because tt is the dummy variable. And then the limit will go from 0 all the way to x. Okay, because I'm starting from 0 and I'm landing on somewhere between 0 and 1. Okay, and that's my x. And then if I do this integration, I can show that this is going to become x squared. Okay, so this is your job to recall your calculus techniques and then do this integration. So you have this x squared. How does this x squared look like? Well, you still have 0, you still have 1, and then you have this fx of x. And here is your x. The pictorial meaning is that you start to integrate this function from minus infinity all the way to x. And this x squared says that you have this function. Okay, so that's your x squared. For anything that is less than 0, you get 0. For anything that is bigger than 1, you get 0. You get 1. Okay, so you go from 0 all the way to 1, and then the more x you go to the right, you will just increase the CDF value because you're integrating this curve. Now, once we have this CDF, I can calculate this probability. The probability that x is between 1/3 and 1/2, that is just fx evaluated at 1/2 minus fx evaluated at 1/3. So you put in the number. What are the numbers? So that would be 1/2 of square minus 1/3 square. So that will give you this number. Okay. So this is the second example of using CDF to calculate the probability using our fourth property. Okay. Now we're going to discuss the fifth property of a CDF. This would involve some efforts. First of all, I want to define this notion of left and right continuous. A function f(x) is said to be left continuous if this f(x) evaluated at b equals to this f(x) evaluated at b minus. Okay, right continuous, you replace the b minus to b plus. It is continuous at b if b plus equals to b minus. Now you may be wondering, how do you actually define this b minus and b plus? This b minus is defined as the limit of your function of b subtract a small value h. Okay, so let me explain it. You have a function here, you have another function here. Okay, so you have a function and then you have a discontinuous point. Now, these two discontinuous points, I will just draw two circles here. Now, let us look at this definition. This is f(x), okay, at b. Now, of course, this is b, and then b minus h. It is a point that is slightly on the left of this b. So this is b, and so b minus h is here. Okay, so this is b minus h. And then now you set this h go to 0. So you set this h go to 0. This gap is your h. And now if you make the gap smaller and smaller, this point is going towards this point. Okay, and so now you say that left continuous, if f(x) of b, which is the point evaluated at b, it has to equal to this left-hand limit. This left-hand limit means that I am starting from the left-hand side and push this point towards its limit. Now clearly the limit is here, and so you will have this. Okay, so the left continuous says that a function is left continuous when you have a solid dot on the right-hand side, okay, or at the end. Okay, right continuous says that you have a function here, and then you start with a solid dot. Okay, so this is called the left continuous. This is called the right continuous. A function is continuous at b if it is both left continuous and right continuous, because if it is continuous, then you would just have this. All right. Okay. So this is right. So this is just continuous. This is a picture illustrating what we have just discussed. Here is the point of B. This is B. And then anything that is on the right-hand side is called the right hand. And then now if you set the h going to 0, then you have the right-hand limit. This point is the limit where h goes to 0. You evaluate b plus h. And here, this point is your limit of b minus h. If your f(x) at b equals to the right-hand limit, this is called right continuous. If this f(x) at b equals to the left-hand limit, it's called the left continuous. Okay. All right. So make a guess whether the CDF is right continuous, or is it left continuous, or is it continuous? Now, for most of the points on the CDF, they're continuous. However, if you have a discrete random variable, you have some jumps, you have delta functions in your PDF. Okay, let's say you have these jumps. Then you can imagine that what happens to the CDF is that when you see a jump, you will just have a staircase. Okay, and so you will have a jump in the CDF. Now we ask, is it a solid dot on the right or solid dot on the left? It turns out that the CDF is always looking like this. Is it a right-hand limit or is it a left-hand limit? It's actually the right continuous, because you start with a solid dot and then you end with an empty dot. Okay. So property number 5 says that the CDF must be right continuous, meaning that you always have this picture. you end with an empty dot and you start with a solid dot. This case is not true for the CDF. The CDF is always like this. Okay, so I put a checkpoint here and put a cross over there. This is property number 5 for the CDF. Property number 6 is about the jump. You have a jump when you have a discrete random variable, or you have a hybrid random variable including a discrete phase. So whenever you have a jump, this gap would define the probability. Okay, so you can see in this diagram, the probability of x evaluated at B is defined as fx at B minus the left-hand limit. Okay, now what is it? In this plot, we have 2 points. This point is fx evaluated at B. Because as a solid dot, fx at B is this point. This is the left-hand limit. It is the limit that I approach to this solid dot. Okay, so I'm approaching from the left-hand side to the solid dot. I will get this fx at B minus. This theorem says that if you subtract these two, which will give you this gap is precisely the probability evaluated at B. Now, all these 6 properties can be very useful. We're going to show you an example of how do we use these 6 properties to convert a PDF to a CDF. Now, this is not an easy example because this PDF includes a continuous range and then it has a discrete state. So essentially, this fx is a hybrid random variable. Let us draw the picture of this hybrid random variable. Its shape for x between 0 and 1 is a straight line, okay, with a slope of 1. And then after 1, it goes to 0, okay? And when it goes to 3, you have an impulse of 1/2. And this is happening at 3. And it's 0 otherwise. So this is the PDF. The PDF has 2 ranges. The first one is a straight line. The other one is a delta function. So we want to find the CDF of this random variable x. Now clearly, if you're only working in this range, you can just integrate and then you can get the CDF. But how do we deal with this range, this delta function, this range, and the range before? So that would be the question. Okay, now for the range that's before, we know that the CDF is 0. So that's very clear. For the range that is between 0 and 1, we have the CDF definition, which is the integration from 0 all the way to x. And then I have this fx, which is my x. I want to replace it by t and dt. Okay. Now this is no stranger because it's just integration from minus infinity all the way to x of your fx of t dt. Okay. Here I'm just substituting my fx, and then I'm limiting myself starting from 0 all the way to x. And then this is just calculus, and I believe that you can do it by yourself. It's integrating this t dt from 0 to 2x. So if you do it properly, you can show that it is x squared divided by 2. Now, how about the range that x is from 1 to 3? From 1 to 3, what do you have? Well, you have a 0 in your PDF, okay? Now, if you're starting from 1 to 3, then what do you have? Well, you are actually integrating this function from minus infinity, okay, from minus infinity to x, okay, and then this x, you have something to put in, and then you have this dt. This something to put in is of course this function, but then the x that you're evaluating at, the x that you're evaluating at is here. The x is bigger than 1, okay, and so now you ask, what is the area under the curve? So go from minus infinity cover this triangle, and then your x is here, so you should start to integrate here, but that is nothing, right? And so that would just give you whatever area you have in this triangle, and afterwards you just don't get anything. So you will just get a probability. You will just get fx evaluated at 1. Why is it 1? Because after 1, you have no PDF, and so you will stay there. Let me draw the CDF for you so that you can see what's happening. For x is less than 0, we know that this is 0. For x is between 0 and 1, you have a quadratic equation. Okay, so this is x squared divided by 2. That comes from part A. And then at 1, you start to stay constant for a while. Okay, so this is 1, this is 3. And now after 3, of course, there will be something. Okay, so that will be something that we need to figure out. But from 0 to 1, we know it's a quadratic equation. From 1 to 3, we know that it is a constant. Okay, so that should be clear from part A and part B. Okay, so this is the picture. We have a triangle, a pulse, and then the CDF looks like this, and then you have a constant. Now we're going to look at this part. This is the part where you have x equals to 3 and x bigger than 3. Let's work on the first case where x is at 3. Okay, so because we have taken care of this range, and so now we're looking at 3, and then we're going to look at things afterwards. Where x is at 3, what is it? Well, when x is at 3, it is actually a jump. There's a jump in my PDF. It's a delta function. And so in the CDF, I will also have a jump. The height of this jump is specified by this impulse. The impulse has a height of 0.5, and therefore this jump would be 0.5. And therefore fx equals to 3 would be what? Well, here it is 0.5 already, right? Because this number is 0.5, and this is probability. This is fx evaluated at 3. Okay, and so fx evaluated at 3 is so this is 3 minus, and then this point is fx equals to 3 plus. Okay, and that's also fx at 3 plus. Okay, so how do we do this? This fx at 3 is actually starting from 0.5, and then you add this 0.5, so that will give you 1. Okay, so you have 0.3, 0.5, add another 0.5, that will give you 1. Okay, so you can see this from the diagram. For x is bigger than 3, what do we have? Well, that should also be clear, because for x is bigger than 3, you will get constant 1. Okay, because you have already integrated the entire function, so that will give you 1. Okay, so this is just the integration from minus infinity to all the way of x, and that is just covering the entire range, and so that will give you 1. Okay, for x is bigger than 3. Therefore, you have this CDF. You have 4 ranges: x less than 0, x is between 0 and 1, x is between 1 and 3, and x is bigger than 3. Now I'm absorbing C and D together because they both give me a value of 1, so they will become the same case. Now, finally, let us talk about how do we retrieve a PDF from a CDF. Because we know that if I have a PDF, I can take integration to get to my CDF. And so it's natural to expect that starting with a CDF, if I take the differentiation, I will be able to get the PDF. And that's indeed true, because by the fundamental theorem calculus, we can show that if I take the derivative of the CDF, I will indeed get the PDF. Why? So you define the CDF as this. This is your CDF. You put the differentiation outside, okay? And look at this. This is just the fundamental theorem of calculus. You apply ddx on this integration all the way to x, and here's a dummy variable. So fundamental theorem calculus says that I can replace my x into here. That will give me my small fx. So this is the PDF. So PDF is really the differentiation of my CDF. If fx is not differentiable at x, then the fx will just give you the probability, which is this fx at this point minus the left-hand limit. So let's work on an example to illustrate this idea. Suppose I have a CDF which is given by this equation, and the CDF has this shape. For anything that is bigger than 0, I have this increasing function. It will saturate to 1. It starts at 4/3. Why it starts at 4/3? You put this x to 0, then you have this number going to 1, and then you have 1 minus 1/4. That will give you a 3/4. So this is a CDF. We want to find the PDF. So we want to take the differentiation of this CDF. When you take the derivative of the CDF, that should be easy. You go through a dx of this function. You should be able to get a formula. And then for 0, that's also easy, right? So for this range, that's easy. Now, at this jump, then you need to know what is the jump. The jump says that I have a height of 3/4, and therefore I should have an impulse of 3/4 at the jump. So let's work on the details. This fx, the small fx, for x less than 0, that is just a d of dx of 0. So that will give you 0. When x is bigger than 0, then you have d dx of your fx dx, which is d dx of 1 minus, let me look at the equation, it's 1/4 e minus 2x. So you can do the derivative, you can show that it is 1/2 e minus 2x. When x is at 0, then you have a jump, okay? Then this is the gap. The gap is just the probability of fx equals to 0, and that is fx evaluated at 0 minus fx evaluated at 0 minus. What is f0? f0, you look at the CDF, f0 is 3/4, so this is 3/4. And then what is fx0 minus? This is the left-hand limit, is an empty circle. This is 0. And so when you subtract, you get 3/4. Okay. Therefore, the PDF can be written as this. You have 3 ranges. For x less than 0, you get 0. X equals to 0, you get 3/4 is an impulse. And then for x bigger than 0, you get this equation. So this is the summary of today's lecture. We have learned about 3 things. First, we learned what is CDF, the cumulative distribution function. It is just the cumulative sum of the probability density function defined by this equation. Okay, so you can think of as area under the curve of this diagram. Okay, so integrate everything up to the point x. The second thing that we learned in today's lecture is that CDF must satisfy a few properties. First 3 properties are stated here, and then the 4th property is that, well, if you want to evaluate the probability that x is between a and b, you take the difference between the CDF. CDF is also is always right continuous, so you always have a empty dot on the right hand side, solid dot on the left hand side. If it's at this continuous point at b, then this gap would define the probability that x equals to b. Okay. The third thing that we learned in today's lecture is the relationship between the CDF and the PDF. Going from PDF to CDF is through integration. Going from CDF to PDF is done by derivative. So I hope you have learned something in today's lecture about the CDF. We will talk about the usage of CDF later in our lectures. For example, we will discuss how CDFs can be used to help us analyze problems about transformation random variables. We will also talk about how can we use the CDF to generate random numbers from arbitrary distribution. Okay. So I hope that you have learned something. I encourage you to work on your homework problems. If you have any question, please let us know. We'll be very happy to help you. Feel free to post questions on Piazza, send us an email, attend our office hours, or just come to our recitation sections. Thank you very much. I hope to see you next time.